A synchrotron is a giant machine in which elementary particles such as electrons are accelerated to extremely high speeds to produce light. There are two synchrotrons in France, one in Grenoble and the other right behind me. Called SOLEIL, it is located on the outskirts of Paris. Let's find out how this impressive machine works and what it is used for. I'm now joined by John Bozek, who is a researcher at the SOLEIL synchrotron facility. Thank you, John, for your time. Before we go into your research project, can you tell us briefly how does the SOLEIL synchrotron work?
Yes, so inside of the concrete tunnel there's an electron accelerator. Those electrons are turning around that accelerator at close to the speed of light, and when they change direction, that's an acceleration force, and that acceleration force causes them to radiate. They radiate electromagnetic radiation, and because they're going very fast, close to the speed of light relativistically, they emit radiation in the X-ray domain. And we use that X-ray here at the synchrotron to do our science with. So you will see many beamlines, and each beamline is kind of coming tangentially off of this circular synchrotron, although it's more complicated than that because there are straight sections with other insertion devices in them. But they give off radiation, X-ray radiation, that we transport down the beamlines to the end stations, and we're surrounded by end stations here to do the experiments.
What does your experiment consist of?
So I'm using the synchrotron radiation to study the electronic properties of simple pieces of matter, whether they're atoms or molecules or nanoparticles, or even in some cases liquid jets in vacuum. We didn't talk about vacuum, so if you look around, everything is encased in steel. All of the experiments take place inside of these steel containers, and inside of these steel containers is nothing. There's vacuum. We pump out all of the air to the point where there's less air in some of these vacuum chambers than there is in deep space. And that's because the X-rays will interact with anything they run into, any particle, whether it's an air particle or our sample, and be absorbed. And so we have to have very good vacuum between the source and the experiment. Then the experiment also takes place in this vacuum chamber. So in my experiments, we inject a sample of gas, an atom or a molecule, and then the X-ray beam coming from the synchrotron impinges on this and ejects an electron because it ionizes it, photoionizes it, because the energy of the X-rays is above the photoionization energy of the materials that we're studying. And by measuring the energy of this electron, we can tell something about what the sort of quantum mechanical properties of the atoms and molecules are, and understand their nature based on quantum mechanics.
Now, such facilities have diverse applications. Can you list some of these applications?
I talked about X-rays, but in fact, synchrotrons generate a wide range of wavelengths of radiation. So, the electromagnetic radiation comes out as waves, and infrared radiation has very long periods of waves, whereas X-rays have very short periods of waves, but the synchrotron generates all of them. So some of the applications use infrared radiation, some of them use ultraviolet radiation, and some of them use hard X-ray radiation. Here at synchrotron SOLEIL, we can use that radiation for various things, studying batteries, studying ancient materials, studying the structure of proteins for developing new pharmacology materials. In fact, there are 28 experiments going on at a given time, ranging from studying a simple atom to studying a battery.